A real valued function of a real variable is a function that takes as input a real number, commonly represented by the variable x, for producing another real number, that is the value of the function, commonly denoted by f of x. So we are very much familiar with a real function, and here f of x is a dependent variable and x is independent variable. So in this graph we have shown a constant function. For all values of x, y takes same value. So in this table we have shown another example of a straight line function. F of x is equal to 2x plus 1. So for different values of x, f of x takes different values as listed here. Now let us define a complex function. A complex function is a function whose inputs and outputs are complex numbers. More formally, we can define as a complex function is a function f whose domain and range are subsets of the set C of complex numbers. Conventionally, a complex function can be denoted in either of these ways. So z is the complex variable. So f of z is the complex function. So f of z is equal to z minus I, or f of z can be represented by w is equal to z minus I, or simply the function can be expressed as z minus I. So for each value of z, if there corresponds to only one value of w, then the function w of z is called single valued function of z. Suppose if w of z has more than one value corresponding to a value of z, then w of z is said to be multiple valued function or many valued function. Now let us consider two functions denoted here as w1 and w2. w1 is equal to f of z, which is equal to z square minus 2 plus I into z. w2 is equal to g of z, which is equal to z plus 2 times the real part of z. So these functions w1 and w2 can be evaluated at any complex number z, and which always yields a single complex number. Now let us find, by substituting different values for z on these two functions f of z and g of z. Let us find f of I, f of 1 plus I, g of I, and g of 2 minus 3i. Now to start with, let us find f of I corresponding to the function w1 is equal to f of z. So which is z square minus 2 plus I into z. Now you substitute I for z in this function, so which gives I square minus 2 plus I into I, and further simplification results in f of I as minus 2i. So similarly, if we perform for the other arguments 1 plus I and 2 minus 3i, we get the results as minus 1 minus I for f of 1 plus I for g of I, and 6 minus 3i for g of 2 minus 3i. So you may check these results corresponding to these arguments of the functions f and g. Now let us define natural domain. So the set of all complex numbers z for which f of z is defined is referred to as the natural domain of f. In the previous examples corresponding to the functions f and g, the domain of f and domain of g is equal to C. It is a set of all complex number. Suppose if we have a function as h of z is equal to z by z square plus 1, the domain of h is the set of all complex numbers except I and minus I, where h of z is not defined. So as we know, for a complex variable, z is equal to x plus iy. X is the real part and y is the imaginary part. So likewise, we can find the real and imaginary parts of a complex function. So let us again consider the same examples of the two functions w1 and w2, given as f of z is equal to z square minus 2 plus I into z. Let us find the real and imaginary parts of this function. So substituting for z is equal to x plus iy in this expression results in a expression as x square minus 2x plus y minus y square plus I into 2xy minus x minus 2y. So we can express this as u of x comma y and v of x comma y. That is, v of x comma y is the real part of the complex function and v of x comma y is the imaginary part of the complex function f of z. For the other function w2 is equal to g of z, which is again equal to z plus 2 times real part of z, we can express by substituting z as x plus iy, which results in g of z is equal to 3x plus iy. Therefore, the real part of the complex function g of z, that is u of x comma y, is 3x, and the imaginary part of the complex function g of z, that is v of x comma y, is equal to y. So unlike a real function y is equal to f of x, a complex function w is equal to f of z is very hard to visualize or very hard to graph due to four dimensions. For z we have x and y as the variables, and for w we have u and v as the variables, resulting in four dimensions. So to visualize a complex function, we plot the complex functions as mappings. In other words, a point in the complex z plane is mapped to a point in the complex w plane. Let w is equal to f of z is a function. It is called as mapping of z to w. This can also be expressed alternatively as z maps to w in this manner. Or simply we can say w is the image of z. So now let us consider an example. Here we have the function w as iz. So z is mapped to w or z is mapped to iz. So we have two planes shown here. One is z plane and the other one is w plane. Let us consider a point in the z plane on the imaginary axis. So under this mapping, z maps to iz. The point on the imaginary axis of z plane will be mapped to a point on the real axis of the w plane. So this point on the imaginary axis on the z plane is represented here by this equation. Z is equal to 0 plus iy. So the real part is 0 and the imaginary part is taking the value of I into y. The function w or f of z is iz, and z is 0 plus iy, and hence f of z is I into 0 plus iy, so which results in the value of f of z as minus y. That means the image of imaginary z axis is the real w axis. Under this mapping, z maps to iz. Now let us consider another example where we have w is equal to z square. That means z is mapped to z square. So we have shown in this figure two planes, z plane and w plane. In the z plane, we have shown the rays starting from the origin as L1, L2, L3, L4, L5, L6, L7 and L8 in different quadrants. So these rays originating in the z plane from the origin are mapped to the rays from the origin in the w plane as f of L1, f of L2 and so on and so forth. Now for the ray L1 in the z plane, we have z is equal to r cos theta plus I sin theta. So the r value is L1 and theta is 0. So substituting theta is equal to 0, we have z is equal to L1. So this ray is mapped as z square in the w plane. So we have z square is equal to r square cos theta plus I sin theta square, that can be represented as cos 2 theta plus I sin 2 theta. So for r squared we have L1 square and theta is 0 and hence we have z square is equal to L1 square. So the ray L1 in the z plane is mapped as f of L1 in the w plane. Now let us consider the ray L2 in the Z plane denoted by the color orange originating from the origin having an angle theta is equal to pi by 4. So for this ray Z is equal to r cos theta plus I sin theta. So r will be L2 and theta will be pi by 4 and hence Z will be L2 into cos pi by 4 plus I sin pi by 4. The components of cos and sin will make this ray starting from the origin denoted as L2. So under mapping as z square in the w plane, we have z square is equal to r square cos 2 theta plus I sin 2 theta. So r square is L2 square and theta is pi by 4, and substituting theta as pi by 4, now we have cos 2 into pi by 4 plus I sin 2 into pi by 4, and hence we have z square is equal to L2 square cos pi by 2 plus I sin pi by 2. So cos pi by 2 is 0, sin pi by 2 is 1. So we have IL square. That means the ray originating from the origin in the Z plane denoted as L2 is mapped in the W plane as f of L2 in the imaginary axis. So from the above observations, we can conclude that a ray at angle theta in the Z plane is mapped to the ray at angle 2 theta in the W plane. Further, the diametrically opposite rays in Z plane is mapped to the same ray in W plane. That is L1 and L5, which are diametrically opposite in the Z plane, are mapped to the same ray denoted as f of L1 and f of L5. Similarly, L2 and L6 are mapped in the W plane as f of L2 and f of L6 in the imaginary axis. Likewise, we have L3 and L7 and L4 and L8. That is, the diametrically opposite rays in the Z plane is mapped to the same ray in the W plane. So now let us consider another example. So here also we consider the same function as w is equal to z square. In the previous examples, we have considered the mapping of rays starting from the origin in the z plane to w plane. Here instead we consider vertical points in the first quadrant of the z plane marked as 1 plus I to 1 plus 4i, and let us see how it gets mapped in the w plane. Suppose if we take the point z is equal to 1 plus I, then it gets mapped to z square as 1 plus I whole square, and if we expand this we have 1 square plus I square plus 2i, and I square is minus 1, so we get 2i or ordered pair of 0 comma 2. So 0 comma 2 is marked in the imaginary axis of the w plane corresponding to 1 plus I point in the z plane. So likewise, we can compute for other values of z, that is z is equal to 1 plus 2i, and we can find z square, that will give the ordered pair of minus 3 comma 4, which is also marked in the second quadrant of the w plane, and we have z is equal to 1 plus 3i as minus 8 comma 6, which is also marked in the w plane. So if you connect all these points, so we get a left facing parabola. So a vertical line in the first quadrant of z plane is mapped in the w plane as a left facing parabola. Now let us consider another vertical line denoted as 2 plus I, 2 plus 2i, 2 plus 3i, and 2 plus 4i in the z plane. So this gets mapped to w plane as z. For z is equal to 2 plus I, we have z square is equal to 2 plus I whole square. So if we expand, we have 4 plus I square plus 4i. That means we have 3 plus 4i, or 3 comma 4 as the ordered pair. So which is indicated in the w plane corresponding to z is equal to 2 plus I in the z plane. So likewise, we can get the values for 2 plus 2i, 2 plus 3i, and so on, and which are marked in the w plane as a second parabola. So the above discussion can be summarized as, in general, z square is equal to x square minus y square plus I into 2xy. These are vertical lines in the z plane are mapped to left facing parabolas in the w plane. Otherwise, f of z is equal to z square maps the first two quadrants of the z plane to the entire plane in the w plane.